In this video, we are going to finish our discussion on the reactions of conjugated systems. And in particular, remember we are talking about these sigmatropic reactions. So in this video, we're going to talk about a particular kind of sigmatropic reaction, which is the 3-3 sigmatropic reaction. So in this one, we have a sigma bond that is between either two carbons or a carbon and an oxygen, whereas in the previous video, we looked at ones where it was between a carbon and a hydrogen. In this one, both ends of the sigma bond migrate by 3 carbons. And so when it is a carbon to carbon, it's called a Cope rearrangement. When it is a carbon to oxygen, it is called a Claisen or Claisen rearrangement. I usually go with the pronunciation Claisen, but I've heard people call it Claisen before as well. So what we see with these 3-3 shifts is this. We have our sigma bond over here between J equals 1 and I equals 1, and it's going to move over here so that it's between J equals 3 and I equals 3. So we can think about the mechanism for this being kind of like this, where this moves over there, this moves over there, and this moves over there. Again, that's not how it's actually happening, but that's kind of a nice way of doing the bookkeeping for this. And so if we look at the Cope rearrangement, this is the one that is between the carbon and carbon. This is a superfacial 3-3 sigmatropic rearrangement, and there can be other substituents on these carbons. So the most generic looking version of it looks like this, where we are just going back and forth between these two things. If we don't have any kind of substituents on it, then we can see that this is not going to favor one or the other of these two molecules because they're both just the same molecule. But if we add other substituents on it, so for instance, if we add a substituent on it that makes it into a conjugated system, then the version of this molecule that has the conjugated system right here is going to be the predominant one that is going to be favored in this reaction because of that stability of the conjugated system. Similarly, if we put something with a lot of ring strain on this, then we can make one of these favorable just by relieving that ring strain. So again, we can think of this as going like that, this as going down like that, and this going over like that, so that we end up with this 7-member ring right here, where this over here with the cyclopropyl group on it is going to have a lot more ring strain, whereas this over here that does not have that cyclopropyl group is going to have a lot less ring strain. So this one over here is going to be the favored species in this reaction. We can do something similar by having an isomerism after the reaction. So these are called oxy-Cope rearrangements. So what we see here is we do the Cope rearrangement right here. So that's going to move this sigma bond over to there. And then we end up with this enol group right here, which can undergo this keto-enol tautomerism so that we end up with this right here. And so this would be in an equilibrium. If we have this get turned into the more stable aldehyde, then it's going to trap the products right here, and so we will end up with that being favored in the reaction. We can sort of double up on these effects by doing what's called an anionic oxy-Cope rearrangement. So now what we're doing is we're going to deprotonate this alcohol right here so that we end up with this oxyanion right there. We undergo the Cope rearrangement, and now we have this product right here, which is resonance stabilized. This can then get protonated at this carbon, and so then we end up with our aldehyde right here. And so what we have going on here is we have this unstable reactant because we have the negative charge on it, and we also have the isomerism, which traps it into this form here. So we are getting both an unstable reactant and an isomerism that traps it as the product in this case. And so those were some strategies for driving the Cope rearrangement forward. Now we can look at the Claisen rearrangement. So again, this is a superfacial 3-3 sigmatropic rearrangement. We now have the I equals 1 carbon exchanged for an oxygen. So we now have an oxygen here rather than a carbon. But the ultimate effect is the same thing. This sigma bond right here between this carbon and oxygen is going to move over here so that it ends up between these two carbons. And so there are multiple different types of these Claisen rearrangements depending on what else is put onto these R groups. So we have an R group there, an R group there, and an R group there. So depending on what is put onto each of those R groups, we end up with a different type of Claisen rearrangement. One of the more popular ones is if we make an aromatic ring between the R1 and R2, and this is called the aromatic Claisen rearrangement. And that looks like this. So again, we have our R1 right here and our R2 right there. They come together to make this aromatic ring. We are going to have these electrons move there, these electrons move there, these ones move there, so that we end up with this. Then we are going to have an isomerization that makes this, because what we see is that this first step is unfavorable because we're breaking the aromaticity on this ring right here. And so this isomerization reestablishes the aromaticity, and so that will actually trap it as the product in this case. As I said, there are other types of Claisen rearrangements, but they are all going to be this 3-3 sigmatropic rearrangement. It's just going to depend on what else is on our molecule right here. But anyway, that was everything I wanted to talk about for the 3-3 sigmatropic rearrangements. I hope you found that helpful, and I will see you in the next one.